Yeah, now we can.
All right, welcome, Praful. So some years ago, Praful came to my office when I was a chair and said, I want to work on something, and nobody in the department works on it. We said, sure, why not? And then another day he comes by a little while later and said, Eric Smith from University of Georgia will help moving forward. I said, sure, why not? So Eric is a visiting professor in our department officially, and he has been helping. And he told me he'll work on Origin of Life with David Bohm. And interesting stuff happened. He told me this is something to do with non-equilibrium statistical mechanics. Long time ago, that was sort of my interest, but then I realized that I can't deal with more than two particles in the initial state. So I gave up on it. But I want to learn from what he learned about non-equilibrium statistical mechanics. All right,
Yeah.
let's go.
Uh,
There are a few cookies if you want that. I didn't have time to make coffee.
yeah, thank you so much, Sridhar. Yeah, so welcome everyone. Thank you for coming. Today I want to talk to you about a gradient descent algorithm that we've come up with, that I've come up with my advisor Eric Smith, as Sridhar just mentioned. And the particular application will be finding instantons, or least improbable paths in chemical reaction networks. But the thing that I want to see, go to the next slide. The thing that I want to, sort of drive home today is that although this algorithm is only for chemical reaction networks, but the theory is sort of more broad, okay? So what I will be doing is, so here's the outline of the talk. First, what about stochastic processes do we want to understand? So I'll talk about that. Then I'll tell you the mathematical formalism of Markovian stochastic processes. Then I'll, quickly sort of run through some basic things which we're familiar with we'll be using tools from physics of how to solve the equation that we get, which represents this Markovian stochastic process. And up until now, there's no mention of chemical reaction networks. Then I will show you the particular Hamiltonian for chemical reaction networks, and then I'll show you the algorithm that we have and some applications, and then at the end we'll talk about some avenues for future research. So what do we want to do? So we know that stochastic processes can be used for modeling all sorts of behavior. The thing that I'm interested in, for example, is the origins of life, but you can use them to talk about biochemical processes, climate, stock market, so on. These are some random slides, some random processes that I just found online. But let's talk about in stochastic simulation. So this is something that I made two simulations of stochastic chemical kinetics with different scale of particles. And by scale, I mean, if you look at the y-axis, you have the counts, right? So, and what is happening is these counts are stochastically changing over time. And if you look at the panel on the left, your counts are around 200 to 600. On the right, they're from 500 to 1500, roughly speaking. So you can see that there are two different scales of stochastic simulations. And by scale, I mean, I'm referring to that quantity. And one thing that you can do now, you can take a stochastic simulation. A priori, you might think, oh, it's all random. But what you can do is you can just plot a histogram. And you will see that eventually, if your stochastic process comes from something that is that has certain properties, your histogram will converge to the stationary distribution. And over here on the left and right, again, I have the two stationary distributions from the two simulations. Now, one thing that you can do, even though those distributions look different, what you can do is you can sort of do a sort of first you can take the log of the distribution, and then you can descale them with a factor v. You can rescale your x-axis with a concentration with a factor v. And now we're beginning to see that there's like there's the structure that is independent of how many particles you're simulating, and that structure is actually pretty similar, right? And of course I knew this because I simulated the data, so I know it's the same one. But what we can actually do more. What we can say is, we can figure out analytically for this particular case, what will this log improbability for a given, and this is drawn from chemical reaction network, for a given stochastic process, in particular a chemical reaction network, what does it correspond to? And in this case, we can find that analytically, and that's the black curve over here. And there's some things to mention right now is that, so if you look at the bottom, the stationary distribution, you write it as an exponential of something that is called as the large deviation function, and that's your S. It's multiplied by a scaling volume. And the fact that asymptotically, so in the limit v goes to infinity, your stationary distribution can be written as exponential of a large deviation function. This is the large deviation principle. And so in this talk, and essentially the thing that I want to convey to all of you is, in the last case, we found out what the large deviation function was for for a particular one-dimensional case. But in general, we have an algorithm to estimate these large deviation rate functions for arbitrary stochastic chemical reaction networks. Okay, and I will talk about the algorithm. That's in the second half. But the first half of the talk, I will first discuss how to obtain the large deviation function for any Markov process using Hamilton-Jacobi theory. Okay. And this is the paper if you want to look at more details. So I hope the motivation is clear. Yeah, any questions? Oh, like where do I get the simulation from? Like what's going on? Right. So this is something I haven't yet told you, but the idea is that there is some rule, and I will exactly tell you what chemical reaction networks are eventually. But for now, it's sufficient to understand that there's some rule by which the population is changing. And it's not just one rule, there can be a set of rules, and you're randomly picking at each time point where to go next. And that's the setup. And you can see that it's a fairly generic setup. And even then we can actually say things which are quite interesting. All right. So next, I want to tell you about the mathematical formalism of Markovian stochastic processes. So first, what are stochastic processes? Or first, what is a process itself? So we have, to define any process, you need the notion of a state. So this state, we will denote it by n, because we want to talk about integer populations. But this n could belong to any r to the d in the positive integer lattice on finite fields and so on. And in the bottom, you can see that this is, for example, a two-state system where you have only state A and state B. Okay. Next, we have a notion of an event. So since it's a process, you have states, and then you have time, and together they create an event. That data gives you an event. Then, since we're talking about stochastic processes, what we will have is a probability distribution on the space of states, and at a given time. So rho is a function which is your probability function. It will take in two values, n and t, for state and time. And so this is the sort of the setup of a stochastic process. Now there's the Markovian aspect of the process, which is particularly given by having something called a transition rate matrix. So the picture that you want to have for what a Markovian process is that the next time step will only depend on the current time step and not on the past, right? So if you look at the bottom left, the joint probability that, suppose you're in state n at time t minus delta t, and delta t is some unit of time, what is the probability that you're in state n prime at t, right? And this will be given to you by a term in this matrix W, and W is a rate, because when you multiply W by the delta t, then you get a probability. Okay, so the transition rate matrix, it is the rate, you multiply it with a unit of time to get a probability. the kind of picture that you can sort of have for what is happening at a global level is you have a bunch of states. Now each state can transition to multiple states given these conditional probability, given it's some transition rate matrix, and that process can just keep happening at each point, right? And this is the thing that we want to track down, and we want to understand what's the structure of this. So one thing that you can do is you can write down a differential equation for how these probabilities are changing with time. So if you look at the and I'm going to make this sort of short, and but the basic idea of this master equation is that the rate of change of probability at a given state n, it is all the ways that you come in from an n prime to an n. So that's the first term on the first equation. And you subtract out all the ways of going out from your state to all of the other states. So that's the second term in this equation. And that equation is called the master equation. It's just defining Markov continuous time because of del by del t, Markov processes in general. Now, but what we can do though is we can recast this equation in what is shown in the second line by using something called a shift operator. And the shift operator, essentially, the exponential of this differential del by del n, if you look at the bottom equation on the bottom, whatever coefficient that you have to this del over del n, that is just how much the argument of your function is going to be shifted by, okay? So, so the key thing that we're doing over here is instead of writing the first equation in terms of two different, we have two terms with probability, we can have a single probability term, but instead we can multiply it by an operator in the beginning, and that's the shift operator. And this should be sort of familiar to us in a quantum mechanics setting, where the derivative is like a momentum, and exponential of the derivative is your translation operator. Is the same idea, and you can make you can extend n to the real line to make this thing work, or you can restrict it to the integer lattice. So that's all fine. But the key thing over here is, if you notice the third line, now all of that, in the sense, the operator which has the shift term and the state information, you can get all of that in the single operator, that's your Hamiltonian, and that Hamiltonian is now acting on your probability distribution, okay? So you get something like a first order, equation, but don't be fooled, like this is highly, I mean, you have these operators, it's not just, it's not as easy, but this is what we have. And this should remind us of the form in which this is del rho by del t is equal to h rho. Now the minute we see this as physicists, we know that we can do stuff with it, right? So and that's what we'll be doing. But first, let me point out a few things just in the master equation that although nowhere have we said that this n belongs to the integer lattice, although we will say that in the future. And this r, if it's a small number, then this approximation, you can expand it, do a Taylor expansion, that'll give you the Fokker-Planck equation. If this transition rate matrix W n to n prime, if it does not depend on what the n is, right, then you get Brownian motion. You can also get Langevin dynamics from this, and all of this is in this reference at the bottom. But I just want to say that this is the sort of broader picture of stochastic processes that we have over here, okay? But now I'll now tell you that once we have this master equation, what can we do with it? Well, we will use path integrals, we'll use large deviations and Hamilton-Jacobi theory to I will explain what this is to actually get at some approximations of solutions to the master equation. And those are the things that we want to understand. It's explained in the beginning. So right. So solving the master equation, we have the master equation at the top. Del rho by dt is equal to Hamiltonian acting on the on the probability function. Now there are multiple games that you can play, which we all know, which we might be familiar with in quantum mechanics as well. But and what are these different things? So we can either, one is we can write down an abstract Hilbert space sort of representation of this wave function, and that's to the left. Or what you could do is you could take your wave function, you can get a generating function out of it. So you can get a moment generating function, which is simply, just multiply z to the n and then take a summation. And now what you get is a function in z. It's a power series in z, right? Or what you can also do is you can take a map, z goes to e to the p, and what you will get is e to the pn times rho of nt. And like a priori, if you haven't seen this might look, why are we doing this? But this will be very familiar to people as partition function, if you've seen that. And then you can take the log of that, and there's something that I will now explain further. But I just want to draw your attention to the familiarity of tools that we have from quantum mechanics, where essentially we don't have the factor of I. Instead of working in integer ladders, we could work on the reals, and then from a z transform, you get the Laplace or the Fourier transform. So there's two ways in which we could approach at solving this equation. And I will give you both of them very roughly because we don't have enough time, but one will be more rough than the other. And this is that one. So one thing that you can do is you can do this sort of construction where you start from a probability function, you take its z transform to get a moment generating function, you take its log to get a cumulant generating function, and then you get its Legendre transform. And this is the thing that loss deviation theory will tell you, is that the probability distribution rho, it actually goes asymptotically in the limit of large v, asymptotically in v, as exponential of minus v times s, where s is that Legendre transform that we have over here. And you might think that this is like sort of something unfamiliar to us, but actually it's not. Even in thermodynamics, if you just replace n with energy, you have a density of, you have density of states or some density function over the energy. You can get a partition function from that. You can take a log from that and get a free energy, Helmholtz free energy. And then you take a Legendre transform and you get something like the Gibbs free energy. And what do we know about the Gibbs free energy? The minimas of that, they tell you what is the state in which your system will be, predominantly occupied by. So it's a very similar thing that we're doing over here, but we have to be more careful because things are not in equilibrium, and we have to actually take care of the fact that things are changing in time, right? So this is one way in which we could approach it. But as you saw, the result was asymptotic. But there's a way in which we can approach it exactly. We can just solve it exactly, and that is using path integrals, right? So we can say that, and since we have this del rho by del t equals h rho, what you can do is you can do the usual thing. You can integrate. You can write rho at a time t in this form where you have exponential of integral h dt. And insert unities everywhere. And the thing that you will get by doing all of this, and you can look at the appendix of the paper, is that the message though is actually very simple, is that so you want to find out, given a probability function at times t equal to like time 0, and suppose you start at some point n0, what is the probability that you end up at some state n at a time t, right? And the only way to find this is by summing over all of the different paths by which you could have reached there, right? So that summation is essentially over here. You have a summation over all of the paths. It's paths in the phase space because it's Hamiltonian and so on. But the picture, but the idea is that you take each paths, but you weigh them, you assign a weight to them, and that way it will be exponential of the action. All right. So it's the same picture, and where the action is given by the thing that we know, which is p dn by dt minus h, right? So the action remains the same. We're going to say that if you want to start from some t1 from point over there to point over there, we have to take over all the paths. We have to sum over all the paths, but each of the paths we're going to weigh it by exponential of the action, right? But now, and this is sort of shown on the left-hand side, but now what we might be interested in is, instead of just doing this massive sum over all the paths, what we are interested in is, suppose you take, you take the saddle point approximation. You ask, what is the path that gives me maximum contribution, right? And that particular path, if you just restrict yourself to that path, then that will be some extremization of this action functional, right? And it'll turn out that it's finding out those extremal paths amounts to solving a min-max or an inf soup problem, where you're maximizing over the momentum assignment at each point, and you're minimizing over the configuration space. And so the idea is that you can asymptotically approximate this integral on the left with just, to just contribution from one particular path, where that path is chosen as the extremal curve for this action functional. Okay. And the idea is, suppose you could do that, you can then write, and you can do this, then you can write the value of the action along this extremal path as the integral of a function. And this is your action function, okay? So we're saying, I don't want to repeat too many times, so please ask me questions, because this is going to be important to the construction that we have over here. But what we're going to say is that there's a particular, along the extremal curve, whatever the action is, it is going to be a function, and that function is your S, right? And this is what large deviation theory was already giving us. So this is sort of the picture over here, that large deviation theory just captures where that maximum is, but you could, in principle, do this complete thing, and professors like people do this on a very big scale on a daily basis. So you don't need to, nothing new over here. So, but now enter Hamilton-Jacobi theory, and I think this is really neat, is what you can do is you can write down the total differential of S. You can just write it, S is a function of Q and T. You can write it as del S by del Q times dQ by dt plus del S by del T. And we know that this thing is equal to the min-max of the action functional, right? Now, all you have to do is just compare the terms on both sides. So you have dQ by dt, the coefficient of that, del S by del Q, that's equal to P, right? So that's the first term. That's the first equation over there. Second one, del S by del T is minus H. That's the second term. That's the second equation over here. And you can plug in the momentum back into the Hamiltonian to get H times del S by del Q, Q. And this is your Hamilton-Jacobi equation, right? So, so the picture over here is that Hamilton-Jacobi equation is nothing, is giving you, like, what it's giving you is sort of how this action changes along the extremal curve. It just so happens that solving for these equations amounts to solving the curve itself. And on the other hand, what you can see now is that the inf soup condition, or the min-max condition, is telling you that your momentum and position must also satisfy certain properties if you just take the variational derivative. And the properties that they will satisfy is dP by dt is equal to minus del S by del Q, and dQ by dt is del S by del P. And these are your Hamilton's equations of motion, right? And so we know if you plug in your Hamiltonian of the form kinetic energy plus potential energy, this is how you get Newton's laws, ma equals F, right? And the sort of picture that I've shown you over here is that there's a version of all of this for stochastic processes. And the beauty of this is the interpretation is extremely clear as to what this means, because we're working in probabilities, right? So what does it mean to find a path that extremizes your action functional? Well, that is the path that will be the least improbable or the most probable. People use this language, least improbable. But essentially, you're just picking out what's the most probable path, and you're finding those. And if you do find those, that's equivalent to saying that A, you've solved Hamilton's equations of motion, B, you've solved the Hamilton-Jacobi equations, at least, for that particular part. Okay. So right. And here's a sanity check. I mean, what I've shown you is how to go from master equation to Hamilton-Jacobi equations. What you could do is you could start from the left-hand side of your master equation and then just use the Hamilton-Jacobi equation and then solve it out and you will get the right-hand side. So this is, of course, not a proof, but this is, you can check this yourself. But now coming back to the main point, what we want to do in this talk, so coming back to the introduction, we want the stationary distribution, right? So we want that distribution that does not change over time. So what that amounts to saying is that we want to find solutions of the action function that do not change in time. So that's amounts to saying del S by del T is equal to 0, right? But setting del S by del T equals 0 means that you're setting the Hamiltonian equal to 0. And what this means is, so let's say you have n coordinates, you have a 2n dimensional phase space. Now, h equal to 0 constraint will give you this 2n minus 1 dimensional submanifold. And what we're looking for are solutions within the submanifold to find the action function for the stationary distribution. Okay, is that logic, like, I hope that logic is clear. If you have any questions, yeah. Maybe let me repeat this. Is that so the idea is that we want to find the distribution that does not change over time, and that means the log of that distribution also does not change over time, right? And that log, we will denote that as nu, where nu is the particular action function which does not change over time. And just by plugging in Hamilton-Jacobi equations, you know that nu, which is also called as the non-equilibrium potential, by the way, that non-equilibrium potential must satisfy a certain equation, and these are your Hamilton-Jacobi equations. Okay, so that's the thing that we have to do, is we have to find a way to solve this algorithmically for chemical reaction networks. Okay, and that's what I will show you next. Any questions so far?
Yeah, I have a question about when you did this saddle point approximation and looked only at the largest action path and kind of threw everything else away. I'm wondering under what conditions is that a good approximation?
Yeah. Yeah. So the question essentially becomes whether this extremal of this action functional, whether it has a unique extremal, curve, or it has multiple ones of those. And in fact, you can have multiple, and in infinite dimensional cases. And this is something that I can give you examples for those. But in typically, like in cases, at least for the chemical reaction networks that I've studied, and there's probably something here to be shown that I haven't yet shown. Like I don't know if people have shown it, but typically it's like you have a unique extremal curve, unless your global geometry is like weird or something, and then you would have to worry about those. But for the cases that we will be working with, there's like a unique extremal curve that we'll be.
There's also the question of when it's unique, how sharp is the peak?
Right.
Like it could be sort of flattened.
Right. So the other thing is, you might not just care about this extremal curve, you might actually care about fluctuations around this extremal curve. And precisely for that reason, because it depends on how sharp this peak is, that you will know whether or not you have these fluctuations which matter or not. And the thing is, and this is the beauty of doing things with path integrals, is this is the exact expression. So, and I can refer you to sources if you want. What you can do is you can do an expansion. So finding that action function is like the 0th order term over here. But using functional determinants and so on, you can also find higher order contributions. You can just keep doing this systematically if you want, what is the breadth around this? Yeah.
So like a distribution with like a single nice sharp peak would be like an ideal distribution to use with this method? Yeah,
okay. Let me go to the stochastic simulation to sort of show this point clearly. So now, your path is going from here to here, right? But again, if you just find out like what is this classical equation of motion, you will just get a path, okay? But based on other factors, you will get fluctuations around that path. And even though this is a very simple case, like it just has one dimension to go, of course it goes straight. But and I will show you a two-dimensional example in the future where it's like the path sort of goes around, and then you might not just be happy with finding the direct path, you might want to keep higher order terms. But yes, but my algorithm is only getting you that direct path. So it's like finding the 0th order or like, the first term that contributes to this.
Such graphs. Each graph corresponds to one. Like the maximum thing you're finding would correspond to one graph. And you see different graphs with different.
Yeah, exactly. Yep. Yeah. And and based on the scale of these things, and those fluctuations might be important to people, right? So okay. So now go to the next part of chemical reaction networks, and this will be fast, although I could talk a lot about this. But first thing is like chemical reaction networks, they're found everywhere. You can find them in cosmology. For example, if you're just thinking of I mean anything which has the form some particle A plus particle B goes to particle C plus particle D, you can write it as a chemical reaction network. In the nuclear fusion in the sun, here's a chemical reaction network for that. Some biology, of course, there's chemical reaction networks inside of us. Now, what is the thing that makes chemical, like how do you define a chemical reaction network? It's defined using three things. First thing is you have a set of species. So for example, in this diagram, proton, neutron, positron, gamma, neutrino, these are species. In standard model particles are species. Then you have a notion of complex. Complex is a multi-set of species. So it is, for example, if you look at the very top, two protons come together, right, to create something else. So the fact that it's two protons, that's a multi-set, and that's a complex. And then they will give, what do they give you? A neutrino, positron, and a deuterium atom, right? So that is also another complex, okay? And then reaction is essentially this going from complex A, like complex Y to complex Y prime. That is what constitutes a reaction. More generally, mathematically, chemical reaction network is a hypergraph where a graph is edges between vertices, hypergraph is edges between multisets of vertices. Okay, so we don't need to go into the detail, but yes.
It also these reaction rates, it's like that.
Yeah.
Depends on the amount of species that you have, how much of each type there are, and the overlap probability, so to speak, right? In order to catch all of those encoded.
Yeah, so there's two things that a chemical reaction network does not itself specify. Is it does not specify the mechanism by which these reactions are happening. And so suppose you wanted to take a quantum mechanical viewpoint of things, then you would have to figure out what is the mechanism by which it's going on. And then there's a rate constant for each of these. Well, I mean, it depends on the mechanism, but there can be other fudge constants that you might have to do, which, because as you said, it could just depend on the population of. Yes, exactly. So you would have to calculate that. And so a particular case that we will be working with, which is okay, so let me go to that now. The particular case that we will be working with is stochastic chemical kinetics or mass action kinetics. And the idea is that it's two things. One, how this thing shows up in the Hamiltonian. Remember, your Hamiltonian just had this term in the front times the transition rate matrix. But a priori, it's unclear, what this transition rate matrix looks like, and it could look like anything. But once you specify a chemical reaction network, it says, look, these are the only reactions that can happen. So these are the only terms in your transition matrix that will survive, right? So what you will have is you will have a summation over all of the reactions, and then you can say that the change, which is R in this case, R can only be of the form output minus input, because those are the only changes that are allowed. And then further on, we can make another assumption, is that in a well-mixed thing, if you need, say, you need two particles of X to come together and create that and make that reaction happen, then the probability of this will depend on, or suppose the reaction is X plus Y goes to something. So the probability of this is how many X's you have and how many Y's you have. So you just multiply the two and then you do that. You have a reaction go through. So this is called like mass action kinetics, because the kinetics are essentially dependent, based on the mass that you have of I don't know what the terminology.
Three-dimensional system and things are moving around, it just depends on the concentrations, I suppose. Whereas if you're talking about reaction on the surface of something, it depends on all sorts of craziness, like how much of what species adheres to the surface there and things like that.
Yeah, precisely. So the thing is, like in a chemical reaction network, there's no notion of space per se, and I might be saying things which are wrong, but we have Professor Kratz in here, so you'll. But you make this assumption of a continuously stirred tank reactor where everything is homogeneous.
Okay.
However, now suppose you do want to take into account spatial inhomogeneity, what you could do is you could label those particles differently, and then you can have interaction terms between them. So you can say all of these particles, they live in site 1. All of these particles, they live on site 2. So you can do all of that thing, but a priori, you're right. Like there's no notion of space which is in here, right? And this is actually, like, this is beautiful to me, because it shows you how you go from a quantum mechanical description to a probabilistic description. Why? Because you're forgetting all of the information about positions or internal degrees of freedom, and all you're caring about is how many particles are there of a given type, right? So of course you're losing a lot of information in that process, and you have this probabilistic process. So it makes sense, right? Okay, so I will run out of time very quickly. So I will not go over things the way I planned it. But the basic idea is you can write down a Hamiltonian for chemical reaction networks with mass action kinetics. You can put them in all of the different ways that I spoke about, where you're dealing with generating functions and so on. But the thing that we are actually, the only thing that concerns us is the Hamiltonian function that you extract from the Hamiltonian operator, right? And that function for mass action kinetics, it takes this form, where you have a summation over all of the reactions, and then you have this shift term with P being your momentum, and then this part over here is it will have a rate constant, which is telling you how much a rate is going forward, times the concentration, times the polynomial and the concentration of your species. Okay. So the thing to note over here is that the Hamiltonian is convex in momentum, right? So you take the Hessian, it's convex. So what that means is when we were talking about supremizing over momentum, we can actually do it because the Hamiltonian is convex. And this is very similar to how we have in like, your usual mechanics Hamiltonian, where the Hamiltonian is quadratic in the momentum. Okay, so now that I've shown you all the ingredients that go into it, now I will tell you about the action functional gradient descent algorithm. But let me just recap what is the problem that we're trying to solve, and then I'll show you how to solve it. So the objective is we want to find the path of least action. By the way, that is also called as an instanton when the action is non-zero. Hence the name of the talk, given some boundary conditions and energy constraint. And so we will be given 2 points in configuration space, where you want to start, where you want to end. You have a Hamiltonian function, just comes from a chemical reaction network. Then you restrict to a constant energy surface. That comes because we just want the stationary distribution, right? And the Hamiltonian looks at that form. And what we want is we want a phase space trajectory gamma star, where the variation of the action functional around this gamma star is 0, or equivalently gamma star is arg in, is the argument of inf sup of the action functional and the action, and this part is clear, right? I just described that earlier. And we want those solutions to this where the action is non-zero. Okay, so here's the algorithm. So the algorithm is essentially so we said we'll start from some point Q0. We want to end up at some point QT. We don't know what the least action path is going to be a priori. Let's just join them with a straight line. That'll be our initial conditions. So you have a configuration space curve. By the way, things in position, I'm calling them configuration space. And with position and momentum, that's called the phase space. This is standard terminology. So configuration space curve, you start with that, with a straight line, for example. Now what you do is, it will be discretely sampled on n of these points to each difference, so this is Q1, Q2, Q3. To each of these segments, what you can do is you can assign a momentum using the supremization condition, and you can assign a dt. You can ask, what is the momentum such that, what's the best momentum such that your particle starts from here and then ends up over here, not particle, the system, and how much time will it take? And you can solve those things, and you get a phase-space trajectory out of that, which has now both position and momentum, and this is called lifting the trajectory. Then what you can do is you can calculate the action functional along that, and let's skip this part for now. What you can ask is, what is the functional gradient around, for this particular curve? And whatever the functional gradient is, you can take its negative, and that in some sense gives you a descent direction, right? So that's just your gradient descent. And you can find, and I'll get to the filtering part later, but you can find a step size such that when you descend in that direction, your action actually reduces, right? So we just want to pick any step size so that the action is actually going down, and then we can update our trajectory to get a new trajectory, and then this thing will loop around, right? So it's just like doing a gradient descent, but it's with curves rather than with points with a function. So a priori, like you might think, oh, this is very straightforward. Why am I giving a talk about this? And but the thing is, if you just do this, you will end up with a lot of oscillatory curves, which will just be garbage, and you wouldn't know what to do with it. And that is because there's a lot of numerical, solving numerical problems over here, plus discretization issues. There's a lot of issues with that. So how you get around that is each time you get a functional gradient, what you have to do is you have to filter the gradient out. You filter it with some sort of low pass filter with some say passband frequency f sub c, and then you're just making sure that this descent is smooth. Then just do the same thing, find a step size so that you're actually descending, update your trajectory, do this again. Now, some things that can happen, as they happen in every gradient descent algorithm, is that you might get stuck in local minimas, right? So what can happen is maybe at some point you find out that there's no epsilon, there's no step size for which you can descend further. What you can do in that case, so if your epsilon is less than some epsilon threshold, or maybe you figure out that even though you're descending, your action is not changing at all. So your action is less than some delta S threshold that you want, and that'll be signs that you've reached some minima. What you can do is you can either update the cutoff frequency at that point. So you can say, rather than just letting these many frequencies in, I'm going to let much more frequencies in and then do the same thing again. Or you can increase the sampling. So you can say, instead of having just 200 points in my trajectory, I want 2000 points, right? Because at the end, it's a continuous curve, and you can do this, you can play this game infinitely. And you're guaranteed to reach the minimum. So some example of how this algorithm run looks in principle, in practice. So you have a curve. So the lightest blue line, which is the straight line over here, this was my initial condition, and then eventually you descend to get this sort of curvy shape. And now how the action changes, you can see that with some descents, action will change drastically, but then it'll stop changing. So then what you do is you update the cutoff frequency, and then you just keep doing this thing again and again. Sometimes your step size can be very low, but you can also just increase your cutoff frequency. And you can see that by iteration 23, I actually get a curve which looks good. But you will ask, how do you know that it looks good? How do you know you have the right answer? And this is the beauty of doing things this way, is that as I mentioned earlier, that the solutions, the least action solutions, they also have to satisfy Hamilton's equations of motion. So what you can just do is you can integrate Hamilton's equations of motion backward and forward And if that integrated curve looks very close to your curve, then you have the right answer. Like there's no second order over there. And so we have a mechanism to just verify whether or not our descent is complete or not. And if it's not complete, just keep doing the same thing again and again. So this thing over here, you can see, you can also plot out how does the distance from this equation of motion changes. And yeah, it'll keep becoming smaller, and you can put some sort of threshold over here. You're like, if I am so close to my endpoints, that's good enough for me, and then that's a good enough action. So so that's yeah.
Or higher frequency components if you're stepping through this loop multiple times. Don't you get back these
Right.
Amplitude fluctuations like crazy?
Yeah, so that is essentially where the game needs to be played, is that you need to let in more frequencies because you have meaningful signal in those higher frequencies, but you need to let them just enough at a time and let it equilibrate. So at each point you increase the passband a little bit, you let it equilibrate, and then you increase it again, and then you let it equilibrate.
So you're controlling that, how much to let in using that delta F condition that you're having there.
Yeah, exactly. And I just for this I just said take some delta frequency cutoff update that you just let in, and whenever it seems like you're getting stuck in a local minima, just update your cutoff frequency and then descend again, right? So some things about this algorithm. The algorithm has sort of three components to it, and this is the cost analysis, just to show you how this works. So the most difficult or costly step in this algorithm is going from a configuration space curve to a phase space curve. So you have to solve these equations at each point to get a momentum and a delta t. But you multiply it with how many points you have in your trajectory, right? Because you have to do this at each point. And then you have to multiply everything with how many times you have to update your cutoff frequency. So that's the next loop, which is get this curve, update the cutoff frequency n2 number of times. But then you might also choose to increase sampling. So go from n to n plus delta n. So that'll also increase your cost. But this is essentially how you would do the cost analysis of this algorithm. Right. So this was the AFGD algorithm. Still have 10 minutes. Now I'll show you some applications very quickly. So this is a chemical reaction network that I'll be choosing, where you have the environment. The environment can create an x2 backward and forward. Environment can create an x1 backward and forward. 2x1 can make 3x1. 2x2 can make 3x2. This is what I call a 2D Schlogel model because and the thing about this model, and the thing about chemical reaction networks in general, and why they're so useful for talking about non-equilibrium or non-linear dynamics, is that they can have attractors. So in the flow field of this system that I have shown, you have a stable attractor over here. You can see all arrows are pointing in. You have a saddle attractor over here. So two directions pointing in, two directions pointing out, and so on. And the kind of thing that one is interested in when we're asking stochastic questions is that, look, if things were deterministic, if everything was going according to mass action kinetics, if you start from, say, this point, is this going to flow into this attractor? Is this going to stay there forever? But in a stochastic setting, there is some probability that it starts over here and ends up over there, right? And that is the probability that we're interested in. These are called escape paths, escape probability. And that's the thing that we want to find is, what is the probability that you start from a stable attractor and you end up at the saddle point, after which the system can do whatever it wants. So I'm focused in on the bottom left attractor over here, and these are some stochastic simulations. So like you're going from here to there, but you can see that two different simulations are behaving very weird, like differently. This one is taking a different path. This one's taking a different path. Of course, it's stochastic, and you can run the algorithm. I don't want to go into too much details, but you can see that your functional gradient does smooth out. And by the way, if you look at this sort of behavior, this is what you get from the algorithm. And if you look at the stochastic simulation, it's exactly this behavior. I mean, the axes are not aligned, but trust me, like it's the same, it's the right thing. And as I said, you can check this against Hamilton's equation of motion. You can also, for simple cases, you can do a stochastic simulation, like a Gillespie algorithm, and you can also check it against stochastic simulation. And you can see that this is the curve that is given, by our algorithm, and it's supposed to be the lower bound of what this action is. So it is lower than either of the stochastic simulations that we found, and they're pretty close. So, and what you can get now is, for a given system which has multiple attractors, what you can do is you can get what are the action, most probable escape paths in their action function for the system. And this way you actually know not everything, but a lot about the stochastic switching dynamics of your system. Because now you know if you're, what is the relative probability, if you ask, of your system being in this attractor versus this attractor versus this attractor. Well, this function gives you exactly that. Okay. And you can do this generally using our algorithm. You can also run this on CRNs, which have like a spiraling nature over here, and it works out. So I don't want to spend too much time doing this, but here's the high level summary is we've solved, or we've given an algorithm to solve a constrained optimization problem, where this is your optimization problem. You're finding min max of this action function. And so let me just bring this to something that people might be more familiar with, is that in physics, generally this Hamiltonian, or at least classical physics, has a particular form where it is quadratic in the momentum. In that case, it's actually very straightforward. You can just analytically find the suprema. So all that we're left with is minimizing over the Lagrangian, right? And this is where people usually see these things from. You write a Lagrangian, and then you find the least action paths from there. But in our case, as you saw, the Hamiltonian was exponential in the momentum. So you couldn't do this analytically, and this is why we had to go over all of these hurdles. And but it's essentially the same theory. It works the same way. All right. Just a few things about what are some future avenues with this thing. I want to first give you like this high level summary for me. What I think are there are two categories of problems in data-driven sciences. So one, there's a forward problem, where you start from a generative model. This could be your chemical reaction network. This could be a Hamiltonian, or physics Hamiltonian, whatever. You get a likelihood function from that. So the model will tell you, will give you a likelihood function. And from there, you predict what the data will be, what the data should look like given your model, right? So this is the forward problem. The inverse problem is you start with the data, then you have to think or come up with a loss function. And from there, you infer what is the generative model that is making your data, right? So these are two types of problems in science in general, in data-driven sciences in general. And what the AFGD algorithm does is, for the particular CRN, for the particular generative model of CRNs, it's telling you how to get these attractor transition probabilities, and then it'll tell you this is how your data will look like if this is your CRN, right? So, what are some very clear extensions of this thing? The first is, and this is something that Professor Dasu just mentioned, is what if we think of all of this in some sort of quantum mechanical setting? So if you have a quantum, if you have a quantum system which is now in contact, instead of a thermal reservoir, it's in contact with like a chemical reservoir with which it can now exchange particles. And in fact, this chemical reservoir, suppose, has some sort of multi-stability, right? So it has many of these attractors. Now, the question you might ask is, how will that quantum mechanical system then behave in the presence of a chemical reservoir that it's in contact with? And application, quantum device in a multi-stable environment. I don't know about this, but I think it seems pretty reasonable. But how I think we could, using just what I've said, attack this problem is, I've shown you how to write the Hamiltonian for CRNs. We already know how to write the Hamiltonian for quantum mechanical systems. Well, whether we can put them together and just solve a bigger gradient descent problem to get that, That is one avenue of future research. The other avenue of future research is, so far we've spoken about reaction networks. Remember, reaction networks were these hypergraphs, but we only restricted to populations. So we said, if your population is on the integer lattice, then you have these reactions. But your population could be, your states could be finite fields, like they could be 0 or 1, right? So that would give you something, and you could ask, can we make another reaction network with that? And can we have it to be stochastic and do all of the things that we did? And now what we have is a stochastic Boolean network. Or correspondingly, you could also ask questions like, rather than your states being in the positive integer lattice, you can ask them what if they're on some compact spaces, and you might get something like a rotational reaction network. And what are some applications of this thing? So if you suppose now want to model how the inside of a cell works, yes, chemistry is a part of it, but there's also gene regulatory systems which have this on-off dynamics. And there are also these biological motors which are inside a cell, which you need to figure out how to do. So having this sort of general theory of stochastic reaction networks in particular, and let me just point out something, that there is a general theory of just stochastic dynamics, and there's a supersymmetric theory of stochastic dynamics. So, and people have done this thing to a great extent, but from what I understand, they haven't yet looked at what if now, rather than considering arbitrary transition matrices, what if we constrain ourselves to just reaction networks or hypergraphs, right? And we could, and that's another avenue of research. And my final slide, I promise, is what about the inverse problem, right? And this to me is extremely fascinating. The question that we want to ask is, suppose you're given some data in a lab, a chemical experiment, biological experiment. Well, biological might be hard. Say a chemical experiment. Can you figure out what is the CRN from which that data is drawn, right? And this would probably be some sort of machine learning algorithm. But what I've sort of told you now in this talk is, suppose this is what your data looks like, right? And there's just some stochastic simulation data. What you can do is you can smoothen out this curve. You can assign a momentum to each of these little parts. And this way, what you're actually approximating, you're saying, look, I have a solution to a Hamilton-Jacobi equation. Now I want to figure out what the Hamiltonian is, right? So that's the question that we're asking. So yeah, you can filter, right. So if we can find the Hamiltonian from the data, I think that'll be very useful, right? So that is about it. Just a few closing remarks. I'm in David Baum's Origin of Life group, and I'm grateful for my friends who are in this picture and not in this picture. Well, some shameless advertising. I also have, so if you want to know more about chemical reaction networks, and so I have some work on that, and I'm very happy to give you a talk for a later time, and I have a talk prepared about geometry and combinatorics of autocatalysis. My defense will be next month, 9th of May at 3 p.m. We still don't know where, but yes, that's all I wanted to say for today. Any comments or questions? The time is 5. It was exactly 5 when
So what will be more? What more will you have present at your defense? Tell us a little bit about that.
Yeah, sure. So as I mentioned, so the stuff that I spoke about today is like 1/3 of the stuff that I've done for my thesis, and so the second third is essentially figuring out, when biologists and chemists, when they talk about autocatalysis, what do they mean? And also, what are some, can we enumerate all the autocatalytic cycles? So that's this work that I have. But the thing that I will really be focusing on for my defense is and this is my thesis, is there's a notion of evolution in just chemical reaction networks that I will present a formalism for. And this is not like because as I just mentioned, the research group that I'm in is the origins of life. So the question that we're sort of interested in asking is, if you understand everywhere from Big Bang to how Earth was made, and then everything from the first cell to modern life, and that's like modern biology. But in between, that's the part that we don't yet understand, right? That's an open question. What's the origin of life? So so my thesis is that if you just with chemical reaction networks with mass action kinetics, even more constraints, we have enough structure that you can have a form of, you can like make precise a notion of evolution in that. And then what is this thing that I am promising you that I will make precise in my defense is, so modern life, it has these, it relies on genes which has these long polymers. The question is, in an early Earth environment where there were only small molecules, how did we get to a stage where long molecules, like long polymers, could be formed and they would stably sustain themselves, right? How could we get to a stage where they could maintain the high population of longer and longer molecules? And that, because like if you think, if you're just thinking sort of thermodynamically, it seems counterintuitive if the things are becoming longer and longer, because things should be becoming smaller and smaller. But at least the thing that I will be saying is, mathematically, I can show you some models, and pretty generic models, where you can have a population distribution with more long molecules, and that attractor will be more stable than the attractor which has a lot of small molecules. So just making this thing precise and showing, giving models for this, that will be what I will talk about in my defense. Right. So in the same paper that I'm writing, I also talk about the limitations of this thing, because evolution in chemical reaction networks is not yet the evolution for biology. And in what sense? And there are two senses that I sort of pin down. One is biological evolution has this notion of there's a notion of Darwinian evolution in biology. And Darwinian evolution has this thing which is like, you need inheritance, you need mutation, and then you need some fitness criteria. But all of these require some sort of spatial inhomogeneity. And as I mentioned earlier, mass action kinetics has none of that, like just by construction. So that's one thing, that we don't have spatial inhomogeneity. So there's only so far that we can get. And secondly, the thing with like genes and proteins and the central dogma is that your genes can somehow tell the proteins what to do, right? They will tell them to fold in certain ways. So this comes as a result of a complexification at the level of chemical reaction networks themselves. Like they're forming certain functional or modular groups which have a certain computation, like which compute something, and they will have a certain function in the ecology, and they will say, look, because this thing is turned on, that thing will now be turned on, and so on and so forth. So nothing that I will say will talk or even begin to talk about how reaction networks themselves complexify. So, but you would need both of these things. You would need a complexification of reaction networks and like forming these functional groups, and you would need spatial inhomogeneity. And once you have those two, then at least for now, we can argue that will give you some sort of origin of life. That is a scenario that will give you origin. And Darwinian evolution and central dogma, I think these two is a pretty strict, like if we can get to that, then I think people wouldn't disagree that that is biochemical life. That's at least the origin of biochemical life as we know it today. Exactly. So the original life had to have that's right. But so that is true, and so that's why I'm saying like my thesis, it does address a part of the origin of life question. Instead, like at least it tells you how to get to big polymers. But the part that it does not get you to is what is the origins of biochemical life that we inhabit, right? And the thing with central dogma, like, there's two ways to actually look at it. I'm sorry, I'm going on and on about this, but this is fascinating. But so as you said, you have DNA to proteins and whatnot. So this is, in some sense, you can see this as information flowing from your genes to proteins. Another way of seeing this is that the proteins a priori could do anything. So the entropy of the protein is a lot, but because of the presence of certain genes, that entropy is constrained. So information is flowing in one way from DNA to proteins, or the entropy of the proteins is constrained because of the DNA. And like, so information one way, entropy one way. And this is sort of the way in which you could think about this, also think about the central dogma, right? And you will see that I haven't, I mean,
Well,
yeah.
I think that's a good advertisement for people to come back. So let's do that. And we can also continue to discuss here and let Eric and others go that are connected.
Yeah.
All right, thank you. Did Eric have any comments?
Yes. Eric, any comments?
Yeah, there are a couple things I can say sort of about effectiveness of the talk. I can keep it short, or I can do it another time. The trick is I gotta not forget.
Yeah.
So,
You can't hear him, but.
Yeah. So I guess, okay, I can turn him up as much as I can.
No, just you just repeat. I think that's.
Okay, I will repeat after you say, because you're not hooked up to the big speaker.
yeah, okay, no worries. So overall, terrific. You put a lot of good content that was correct in a really small space, which is really difficult. It's great that you're in a physics department because it allows you to take things for granted about your audience that save you orders of magnitude in time. I don't know who all will be in your defense audience because you're doing interdisciplinary work. So you'll want to get sensitive feedback from people who have different background sets and figure out how much can be done to sort of provide depth of content for the people who know where the front of hard problems is, but also be as comprehensible as possible to people who want to know why this is interesting for what they care about. So I won't try to judge that. You'll have interdisciplinary members who can give you good feedback on that. You have the slide where you introduce the path integrals. I would recommend a little comment that I think you didn't make. In the first couple slides, you had said a lot about the equivalence of stochastic and quantum formulations. You kept the treatment somewhat light, which is necessary. But the thing, if you're a psychologist, anyone listening to a lot about Schrödinger's equation is primed to notice the letter I. On your slide where you introduce the path integrals, you use I as a time step index, and that can throw your audience. So I'd recommend that you say at some point, this is all lovely. We're not going to say anything more about quantum mechanics in this talk. I need an index for time steps, and I'm going to use I, don't be fooled.
All right, should we get going?
Yeah. Okay.
Waffle.
These are small technical things. If you don't want to repeat them, it doesn't matter.
Yeah, you can
Yeah. Yeah.
There are a couple places, and this is a matter of presentation effectiveness. When you're straining to get material in, it's easy to go into a kind of a run-on mode where things follow one another, tumbling one after another. And it's just almost impossible not to do that yourself, but